Although it may not be obvious to the average person, organic chemistry is absolutely everywhere. From the paint on your walls to the gasoline you put into your car, it's incorporated into our everyday lives in an infinite amount of ways. In fact, it's almost impossible for a person to go a whole day without coming in contact with an organic product. Soap is a primary example, and it's something everyone uses every day. Well, we can hope. In general terms, a soap is the alkali salt of a long-chain fatty acid, typically derived from animal fats or vegetable oils. Solid soaps usually consist of sodium salts, whereas liquid soaps usually consist of potassium salts. If you look closely, you will notice that this triglyceride is basically just a bunch of esters, or R-COO-R' groups. We will see that heating, around 80 to 100 degrees Celsius, in the presence of a strong base, will cause these triglycerides to undergo a base-promoted ester hydrolysis reaction, or saponification. This reaction is actually a very simple organic reaction consisting of common mechanisms. A nucleophilic attack on the ester will first kick the electrons from the double bond onto the oxygen, which is highly electronegative and therefore able to support this extra charge. This results in a tetrahedral intermediate. In order to stabilize the molecule, the extra electrons on oxygen are going to come back down and kick out the OR group, resulting in a strong base that will then deprotonate the acid to form a carboxylate anion. But where did hydroxide, our strong base, originally come from? Well, it was ionically interacting with some sort of alkali cation, like sodium or potassium, right? So finally, the sodium cation will become attracted to the carboxylate anion, forming an ionic fatty acid salt, the soap, and a glycerol molecule. So why does this process allow soap to clean? Well, it results in the formation of an amphipathic molecule, meaning it contains both hydrophobic and hydrophilic parts. The process of saponification results in long, nonpolar hydrocarbon tails that are hydrophobic and polar heads that are hydrophilic. This process helps soap to clean. A quick side note, soap is also a surfactant, meaning it works to reduce the surface tension of water in order to increase its ability to clean. You see, water molecules tend to want to bond to each other rather than to other surfaces because of the strong interactions that are formed between them, all that hydrogen bonding. Put simply, water's force of cohesion is stronger than its force of adhesion. This is why water can form those little droplets. Anyway, due to its amphipathic properties, soap can act as an emulsifying agent to wash away oil, dirt, and grime. Remember that rule of thumb, like dissolves like? Well, that's pretty much what occurs here. The polar heads of the molecules will become attracted to water, but the nonpolar hydrophobic tails will not interact with water, but are only attracted to each other through London dispersion forces. This causes the tails to cluster together while the heads remain bonded with water, forming a micelle. The oil-loving hydrophobic tails can now trap or dissolve the oil particles within the center of the micelle. And because the heads of the soap molecules are charged, the micelles are still dissolvable in water. Remember, like dissolves like. Then once some mechanical energy is applied, the oil, dirt, or grime can easily be washed away. Most of the time, soap is a very successful cleaning agent, but unfortunately its effectiveness is reduced when used in hard water. This is because the ions present in hard water, mostly calcium and magnesium, react with the soap to form an insoluble precipitate known as soap scum. This scum can build up on surfaces such as baths and sinks, which just completely ruin clothing and is extremely tough to remove. Detergents are synthetically made to avoid this problem. Using propene, followed by a series of complicated reactions, detergents are created, and the end of the molecule will consist of a sulfonate, or more commonly a sulfate, anion, rather than a carboxylate anion like in soap. When the ions in hard water interact with detergent molecules, the new substance is still soluble in water and will therefore not leave behind that scum. Soaps and detergents have their obvious benefits. Their invention served as a first huge step into public health. They allow us to clean multiple surfaces such as skin, clothing, and hard surfaces with much less effort than required with water alone, and they add a disinfecting aspect to cleaning as well. Some gentler detergents are even being used to help injured animals after oil spills. So maybe next time you're washing your hands or doing your laundry, you'll have a little bit more appreciation for these amazing organically synthesized products.